All right, so this is an alternating series test intro. So I've got three alternating series here. So what are they? Well, if you were to plug n equals 1 in here, you would get 0. And so that first term would be positive. And so we're going to end up with this: 1 minus a half plus a third minus a fourth. And it will just alternate that sign as it goes off to infinity. If we start it with a positive n, just n here instead of n minus 1, then that first term would be odd, giving us a negative 1 plus a half. So you can alternate it by having the first one negative or the first one positive by doing an n or an n minus 1. And the n minus 1 and the n plus 1 give us the same thing. Because if I were to plug in 1 again, that's 1 plus 1 is 2. It's an even. And an even exponent is going to give us a positive right there. All right, so these alternating series have a converging test. And so we have our alternating series here. And so the b sub n is the thing that we are multiplying that negative 1 to. That b sub n has to be positive, and it needs to be decreasing, which means the next term needs to be smaller than the previous term. And then the limit as n approaches infinity of b sub n also has to be 0. So if these conditions are met, series converges. The series does not tell us about diverging, only converging. And b sub n technically is just that it needs to be eventually decreasing. So you can see here that from right here to here, right, this converges. And so we can do that sum here of n equals 1 to, say, 3, right, of our a sub n plus the sum from n equals 3 to infinity of the a sub n. You can break it up into its parts. So this is our a sub n. Right, and so it can add them all up, and then up from here to here, this is already converged. And so if we can show that from here on is converging, then the entire series converges as well. So this is just basically means that it eventually decreases here. And then we can use the alternating series test on it. It doesn't have to start at 1. Okay. So here is our series that we're going to show converges or diverges. And all it has to do now is meet those conditions. So b sub n. So our b sub n here is that 1 over n. And we know that is greater than 0. Right there, it meets that condition because it's an n, and we're plugging in n's that are greater than or equal to 1. So as you plug in those positive numbers, it stays positive. Number 2, b sub n needs to be decreasing. So let me zoom out. So we could take the derivative and show that it is negative, which would work as well. But it's quicker just to see, if you can use it, that b of n plus 1 is less than b of n. So if we have b of n plus 1, that would just be 1 over n plus 1. And our b of n is equal to 1 over n. And so you can see that this one is less than or equal to, if you want to put it on there as well. But you can see that it is decreasing. And so part I, this is decreasing. And if you made it into a function, f of x equals 1 over x, our f prime of x would equal negative 1 over x squared, which you can see is also decreasing because it's negative. All right, so now we just need to show that the limit as n approaches infinity of our b sub n is equal to 0. And that's very quick because that's our definition, 0. So if you notice, the 1 over n, by the way, is a harmonic series, which we showed earlier was divergent. But making it an alternating series means that it is convergent. So you just have to make sure that it meets both of these conditions with a b sub n greater than 0, and that it's decreasing. You can use the n plus 1 if it works. If it doesn't, use the derivative. And then show that the limit is equal to 0 and it's convergent. This does not show that it's divergent, and we'll see that in the next video.